Okay, so hey everybody, welcome to the Python DeCal week 10, baby. Only a few more left. Today's Monday, April 5th. Yeah. So we have a fun little lecture for you today. We're going to talk a lot about research and stuff. That'll be good, a little bit of career development. I got some stuff I want to talk about first, though. The attendance form's right here. Yeah, we're going to talk all about astronomy research. And here's a little meme for you. I think Elon put this one on it. I don't know how funny it is, but it's pretty true though. Yeah, I'm not gonna read it to you because then it wouldn't be funny. Um, so some announcements. Homework 7 is going to be due Wednesday before lecture. That's 2 days from now. And remember, that's a CV. That's just writing up your own CV in LaTeX. And then yeah, so it has to be done in LaTeX. There's a file on B courses under the homework section that is like a full prompt. It's kind of like a normal homework problem set that you might have in your other classes. Make sure you take a look at that before submitting your CV. It needs to adhere to the guidelines that you set out on that file. Keep working on your final project. You know the deal. Don't slack off. Don't save it for the last week. I promise you, it's going to turn out really crap if you do. Make sure you work on it at least a bit each week if you can. Treat it like a full-on, like it should feel like three or so coding homeworks from this class. So just keep that in mind when you're doing it. It should take a significant amount of time. So just make sure you space it out and don't save it for the last minute because it won't be great. And I want you to have something really cool to show for when you pass this class or when you finish it that you can show when you go to apply for research. So please, please, please make sure you spend time on it. It will help you out getting research positions and so on. Don't wait till office hours just for help, especially when we get later in the semester. You can always just send us an email too if you need things. I mean, come to office hours if you can. That's the best way because we're in person to help you. But if you absolutely need help with your project right away, or you get really stuck and you don't feel like you can wait a week or whatever, or half a week to come to office hours, we can arrange meetings too. But remember, there's an office hours like every day of the week. So I think it's every day of the week except like Thursday, or no, yeah, except Thursday, right? So there should be like an office hour almost every day of the week. So please come if you can. If not, then ask for help. Take advantage of Discord. We have a whole Discord server. Thanks to, I can't remember who set it up, but thank you to whoever did that. I think it might be Asher or Megan. Can't quite remember. But yeah, if you have questions, ask them on there too. And we'll do our best to respond, or other people in the class can help you. And then yeah, the earlier you have a problem solved, the better. Just want to ask before we get on with the rest of the lecture, if you feel comfortable, please go ahead and turn on your camera. You don't have to if you don't want to, but it always helps it feel a little bit more like classroom when I'm teaching, and I greatly appreciate it if you would do that. But you don't have to if you don't want to. Cool. So we're going to do breakout rooms. Luckily, there's enough people here today. So have you started coding for the final project yet, or at least tried to start? It's okay if you haven't, but just talk about that. How nervous are you, like on a scale of 1 to 10 about your final project? Do you think you're going to be able to do it? If not, talk about your nervousness levels maybe. And then have you started LaTeX in your CV yet? What has been a challenging part of making your CV so far, or something you don't understand? So that we're going to talk about those in our breakout rooms. I'm going to leave these on the screen for a little bit longer as I make a breakout room. I'm going to pause it. Okay, so hopefully that was useful. Hopefully it made you feel better or not. I don't know, but hopefully I had a good time. Let's get into today's stuff. Let me share my screen. Or yeah, okay, we're already sharing our screen. Cool. Everybody can see the slides. Good. Okay, cool. Let's get to it. So we're going to talk about research today. I made this meme. I hope you enjoy it. It's not super funny, but it's kind of fun. We're going to talk about kind of like the overall structure of research in the astronomy setting or astrophysics setting. How do you do it? How do you go about it? Because a lot of people in this class probably don't have research, or you're just doing research through ULab, and you haven't gotten your full-on like research with a professor or like a postdoc yet. So we're just going to talk about that a little bit more in depth in the whole process of it, so you're not quite in the dark. So this is kind of the overall roadmap. It always starts with a scientific question. And there's usually like 3 ways of going about getting data to work with, to analyze. Usually somebody writes a proposal and then they get like they're allotted special time, either on a supercomputer to run like a simulation or something, or to get a telescope like Keck for like a night, and then they can take data and collect like brand new data and then analyze that data. Or you could download large public files of data from public science teams like Gaia. You may have heard of the Gaia satellite or LIGO. They have public data that you can just freely take and analyze. Or you could build a new instrument. This is very rare in astronomy, but there are teams that do it, whether or not you're maybe in just Kalu's group, building adaptive optics systems, or Professor Lee's group, or Adrian Lee, who's building like cosmology detectors and stuff, and they're trying to make new data, take new data with that. So there's kind of like those three pathways. Once you get all your data, you analyze it, try to answer your question, whether or not it's true or it's false, or there's a new thing to talk about, whatever it may be, you analyze the data, and whatever your results are, you write a paper about it. You write a research paper, and that paper, once you finish writing it, you send it to a journal. It gets refereed by other scientists in that field. So if you write a star about gravitational, or you write a paper about gravitational waves, they're going to have at least a professor or somebody who's an expert in that field read your paper, critique it, say if it's bogus or if it's good, give you advice on how to make it better, and then it gets accepted, and then eventually it's published, and it's like a full-on published article in a journal, like a magazine would be. So it's very cool, very long process this is. Undergrads typically only do this part that I highlighted in green. Usually we're not quite at the level yet where we can ask a scientific question that's useful. That comes with a lot of experience and knowledge about a field, especially with today's kind of structure of how to answer a scientific question. We're pretty deep into like collaborative astronomy right now. It's rare of the days that you're just like Einstein and you sit in a room and you come up with the theory of gravity just out of nowhere. It's pretty rare that that happens. So nowadays you kind of need to know what's going on in the field that you're working in, know what questions are valid, which ones have already been answered, which ones need answering. So that's more of like the job of like a postdoc or professor, somebody who already knows the kind of questions to be asking. And then they always write a proposal because you kind of need like a reputation. It helps have a reputation, and you need to know how to write a proposal. And this is very much like a postdoc, a grad student, a professor type thing to do. Undergrads almost never write proposals because it's a lot of money on the line, and they're not usually willing to give that to like an undergrad. Like for example, for a night on Keck, it's on the order of millions of dollars that the school is willing to fund for you. So I mean, obviously they want like somebody who's well established as a scientist, so they tend to go for people like professors and PIs and stuff like that. But we usually come in here once there's data. We usually either collect the data. If you're on a group like Alex Filipenko's group, you collect it with a telescope. Or there's other groups that do that. That's just one that comes to mind. Some research projects for undergrads typically involve downloading data from Gaia to compare to data they take with a telescope or something, or trying to see trends with data. And then some groups, like in Jessica Liu's group, you can work on like adaptive optics instruments and build new stuff for telescopes that will be taking data with. Then undergrads always analyze, and that's like part of your research project is definitely going to be analyzing data. And then usually you get to write a research paper at the end. And if you can get like a first author or second author paper out, then you're in good business. That's what you want to do. That's how you want to prepare for grad school. The more research, the more papers you can write, the better. If you can get like a first author paper out before you go to grad school, you're in pretty dang good shape for grad school. So yeah, it'll definitely help your chances of getting in greatly, and make you a top candidate if you can write a research paper that's published. And then analyzing data is all just coding. Well, that's like basically what we talked about this whole entire semester. You guys will be well prepared to analyze data. You've learned about things like matplotlib, numpy, scipy, curve fitting, right? How to use astropy, how to use pandas. You've learned how to take in large amounts of data into a Jupyter notebook, play around with it, make arrays with it, curve fit your data, see if a model works with the data that you took. We talked about that pretty well. You know how to plot, make really pretty plots. If you look at the plotting guide, you even know how to make animations now, thanks to the lecture that Isla and Emily gave and the notebook that Isla, Emily, and Raphael made. for y'all. So that's a lot of stuff you guys have under your belt now for coding skill, for analyzing data. And this is kind of what people are looking for when they take in undergrads for projects. They want to know that you can at least code data, or like code and analyze with data. Yeah, I can't speak. Analyze the data that comes via coding. That's like a very important skill to have, and you guys should all have that now after you finish this class, and showing that you have good Python skills, either by writing a simulation or taking data projects or doing data analysis projects. It's all good skills, and that is very marketable for an astronomy researcher. So there's different types of astrophysics research or astronomy research. There's three kind of head branches. We got theoretical, observational, and instrumentation. These three fields do have overlap, but namely when you do theoretical, that's like what we think of as like analytical pen and paper theory, kind of like very similar to like what you do in your homework assignments. Basically, you're like thinking about a problem, you're trying to answer it with math and physics equations and stuff, and you come up with theories to explain what's going on. And then computational astrophysics, that's like writing simulations and stuff. That's kind of all in the same branch as theoretical. Instrumentation, developing instruments for general use. Not always for science, but definitely science is usually the main goal for instrumentation research. The overlap, and then there's observational astronomy. It's pretty obvious. This is collecting data, observing the night sky with telescopes and whatnot, and collecting and analyzing those observations and seeing what you see out there, or I'm just trying to understand what you see out there. There's the overlap regions, experimental cosmology. That's like trying to tie in building new instruments and stuff, whatnot, to observing like cosmology, trying to understand what's out there, or building telescope instruments to help you do better observations, make different observations that weren't previously possible. And then the last bit of overlap is between observation and theory. This is like data analysis of like computational simulations or data sets, like observational data sets. So maybe you're comparing like a simulation to data from the night sky. So maybe like I'll show an example later, but yeah, like you're trying to compare like your theory results from a computer simulation to like real telescope data. And if they compare, if they disagree, you're trying to understand that. And that's kind of the overlap between theoretical and observational. Each category is really well studied at Berkeley. There's lots of professors with different projects in each and every one of these. Certain professors are more theoretically based, others are observational astronomers, and others are instrumentation astrophysicists or astronomer people. Yes, scientists, that's the word. Cool. So before you do any actual research, though, you always have to start somewhere. And that somewhere that you start is with the literature. So you need to read about the topic you're going to be researching in order to have any idea what's going on. Because oftentimes the stuff you're researching is not really going to be in a textbook. I mean, yeah, the basics of it, like if you're going to study something like, I don't know, gravitational waves. No, not even gravitational waves. Let's go a bit different than that. Let's say you're going to research galaxies, right? You want to learn about galaxies. You'll probably learn about that in your Astro 7A, 7B classes and everything. But you probably won't be able to learn anything about the question you're trying to answer in your research project, because that research project is very cutting edge. I mean, it's by definition, research is exploring the unknown. So there's not going to be anything really out there other than research papers that people are publishing kind of recently to try and understand that. So the two places you get literature or research papers about whatever projects you're trying to answer or trying to research, the way you find anything about any of it is either through arXiv or the astrophysics data system. Both are very useful. The difference is arXiv is like updating every day. It's preprints of papers. So these are not published papers yet. They're expected to be published. They're like probably either just submitted or going to be submitted soon for publishing, but they're not quite published yet. It's kind of like the beginning access. There's more than just preprints of research papers though. There's many different topics. I mean, arXiv is huge. There's branches of arXiv for medicine. There's branches of arXiv for astronomy and physics and so on. And there's even lecture notes for like classes that people teach. If anybody knows who Sean Carroll is, because you're a bit of an astro nerd, a theoretical astrophysics nerd, his notes are on general relativity are even on there. But yeah, and then there's the astrophysics data system. This is like a very specific only for astronomy astrophysics research papers, and you kind of it lets you create bibliographies, and you have very customized search engine, and all astronomers use it. So let's go ahead and look at arXiv really quickly. Can everybody see this? Cool. So arXiv.org, it's fantastic. Let me show you a little bit how it works. These are all the different branches. There's high energy physics, there's math physics or mathematical physics, nonlinear science, nuclear theory, so on, quantum physics even. But we're astrophysics, that's kind of us. And usually I just go ahead and search, but there's different branches of the astrophysics. So there's like a whole subpage, kind of like how Reddit works, for like astrophysics of galaxies. There's one for cosmology, Earth and planetary physics, astrophysics, high energy, instrumentation, solar and stellar astrophysics, all these different kind of sub branches of the astro archive. But for this case, I'm just gonna, well, we could just click on it. Let's say we want to learn something about galaxies. Let's find new research papers on galaxies. This is everything submitted for today. These are all papers that have just been submitted today. And we could pick on literally any one of these. I don't know, this one might look cool. Magnetic field across whatever, we can click on its PDF. So this is a research paper. If this is your first time seeing a research paper, huzzah. If it'll ever load though, it's probably a big one. Oh, there we go, okay. It's loading. Oh man, give it a sec. There we go. Ew, oh no, this isn't done in LaTeX, we're not looking at it, sorry. That's not allowed. Hopefully this is actually, I don't know. Well, I know one that will work. You can search for different papers either by by author or by title. So I'm just gonna search for a paper that I know well. This is by somebody in a research group that I'm in. Let it load for a second. Anyway, you can search for research papers on arXiv. They're free, which is nice. You don't have to go to the pay like journals or whatever to look at it. This is a research paper written by Hoffman and other people et al. It's about like variable stars in M15, and you scroll through it, and this is what a research paper looks like. Some pro tips for reading research papers, because you will be doing this constantly. This is like a huge part of research. It's always the very beginning, usually, as you start reading like 5 or 6 papers on whatever it is you're looking at. You'll notice that they're really long. They're like 20 pages long, usually. This one, it happens to be kind of short, but there are many research papers that go on to be like 50, 60 pages long sometimes even. And you definitely are not expected to read all of it in depth unless you're literally trying to recreate everything they're doing. So in that case, if you're just trying to understand the paper, the typical way I do it, read the title first, read the abstract. This is like the basic summary. Typically, this has a lot of words that you don't understand. If you really want to be in good shape, you can read the introduction, which is usually a page or 2 long, tops. And it has lots of information about background information. So if you want to get really well read on a topic, like our Lyrae stars, for example, you usually read the introduction and you'll have a pretty good knowledge of what's going on, especially if you do it for like 4 or 5 papers. But it's not always required. And a lot of times, if you're just skimming through papers, you don't even read the introduction. And then you start looking at the plots. Maybe look at the subsections that are like the titles of the subsections that you're interested in. But usually you look at the plots. Astronomers always look at the plots. So your first kind of goal after reading the abstract should be to understand a plot, like this one. Read it, read around it, try and understand what it means. Usually the plots carry all the information. Somebody once told me that a picture is 1,000 words. It's very true in the research papers. In fact, I would say almost all the information is summarized in the plots to a degree. So if you can understand the plots, then you can understand basically the whole paper. And all the text around it is usually just details of how they did that, how they made those plots. So they have lots of diagrams and whatnot of data that you can look at and so on and yada yada yada. Like what in the world does this whole thing mean? Well, you read about it, maybe you read around it, try and understand, see where it's referenced in the words, trying to understand what's going on, and you come to a conclusion of like what this is. And if you could do that, if you can understand all the figures in a paper, all the pictures, then you're in really good shape, and you pretty much have a good understanding of that paper. And then if you really want to, I also really like to read the conclusion and future work section or the discussion section. I don't think this paper has a discussion, but usually they have like a conclusion and a discussion section. The conclusion is really helpful, and the discussion is how you find questions that haven't been answered yet. So if a paper says, in the future, we are thinking about trying to answer this, that should be a good indication of how you can think of a question to answer, or do a follow-up research on that. So discussions are very useful and conclusions are very useful, and you skip the rest of it. Skip all that body. It's very not important for your basic understanding of a research paper. Yeah, this is a research paper. You can find them on arXiv. Similarly, where is my slides? Can everybody see the slides still? Cool. You can also go to the Astrophysics Data System. This is we call this ADS for short. It's taking a while. Give it a sec. Maybe if I refresh, there we go. So this is like a search form. You can do a very specific search by author, the object in it, the publication dates, when and where, the title, and so on. Let's just do one on, oh, I don't know, magnetospheres. Something interesting, cool. We could search it, but you can have a really detailed search if you want to. You can specify what years you want it published. So let's look at anything greater or newer than 2010. We can pick certain authors that are prevalent. We can make sure that it's only in astronomy. We can make sure it's a refereed paper or a non-refereed paper, meaning it's published or non-published, basically. There's a lot of other specifications you can add here. So I don't know, we could find, this one looks kind of neat. And it'll take you to either its published paper link or its archive. Yeah, no, it's a gross one. Not well done. See how strongly I feel about latexing? Let's see. Hopefully this is a nice one. Oh my gosh, I keep getting unlucky with like papers. People. Yeah, let's do refereed paper. Limit to only refereed papers. And maybe we could do, actually, we'll look up a paper from a specific person. So if I want to find a paper by this guy named Jim Stone, and I want to limit to him, I only want astronomy, we can find like some crazy equation of state of hot, dense, hyperonic matter in the quark meson. Wow, that's a bit much. And we can go check it out. This takes us a link to its publisher page, so we probably won't be able to look at all of it, but nonetheless, you can go around. You can read an abstract if you wanted to read more into it. I believe you can like get the university to like bypass this, so you don't have to pay for it. But usually I just go to the archive links because it's free. But I'm trying to find like a good second paper. Give me a second. Aha. Okay. This is gonna work. Whatever. I guess it's not latex, but whatever. Anyway, you can read research papers about whatever it is you're looking at, and so on. So that's ADS. It's just a very specific thing. A couple of useful things about ADS is that you can get what's called a bib code, and you can do a lot with a bib code. It helps for citing, and when you write a research paper, citations, so that you can just make LaTeX do it for you. You don't have to actually sit there and type the MLA format or whatever it is. Bib codes are super useful. Definitely don't ever want to have to write those by hand, so use bib codes for that. And then it takes you links to archive and so on, blah, 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 blah. What else was I gonna say? And then, yeah. And then you can also look at different, or you can like follow different authors and so on about their stuff. But anyway, that's enough about reading literature. I think you get the point. So long story short, you need to use these two sites to read lots and lots and lots and lots of research papers to get background information about whatever it is you're researching. Is there any questions about any of this so far? Cool. If that's not the case, then let's move on. So now we want to know how to do this part. How do we access data? How do you how do you download public data? How do you collect data? Well, I can't really show you how to collect data, but how do you get like data from a simulation? How do you get data from a telescopes and stuff, or all that? How do you get the data to analyze? That's important. So we linked some important places for you to check out if you ever want to check out data. So there's these three big archives that almost everybody uses. They're Vizier, Simbad, and Gaia. So we'll just go one at a time through everything. Let's start with Simbad because it's my favorite. So Simbad is really cool. It lets you find basic information about whatever it is you want. So you can search it up by its coordinates. If maybe somebody gives you an RA and declination, you can find that, find it by its coordinates, or you can just do a basic search or by some identifier or whatever. But I just want to look up maybe M15. This is a globular cluster, and we can take a look at it. So this is M15. This is what the survey has. It's a globular cluster. It's just a cluster of tons and tons of stars. A lot of them are pulsating and getting brighter and dimmer through time in like an oscillatory fashion. But you can keep zooming out and you can look at, this is like a whole survey of like the entire night sky. So you can really zoom out, take a look at whatever things are. This is pretty cool. I think this is really sick. But anyway, that's one thing I like about Simbad a lot. And also with Simbad, there's lots of information. It has like coordinates. It has like flux, or it has like velocities and stuff. It has links to all sorts of like papers and stuff to check out more information about it. Yeah, and then there's all this stuff. There's lots of stuff to talk about, but not enough time. Unfortunately, I'm going to have to skip through a bit of this. You can see what papers it's referenced in. So if you wanted to, you can take a look at research papers that talk about it, see their analyses on this object. This is M15. This is a particularly really dense object of information because it's a whole globular cluster and there's millions of stars inside of it. So we're going to move on, but Simbad is really cool. It basically lets you get basic information about an object. You can also get data from papers and so on through Vizier. Is another one. I don't know it quite as well, but if you have a bib code, you can paste it right in here, or you can look up like a research paper by its name or whatever. And if that paper has data that they took, let's say they have like a data table of lots of information and stuff that you want to take and work with yourself, well, you just copy and paste that the bib code file name, or like the bib code reference name to that research paper in here, and it'll spit out all their data, and you can just download it and play with it. I don't have time to do all that because I spoke a little bit too much about literature, but if you're curious, please go ahead and try it out for yourself. The slides will be posted, and you can click on this link and try and pull up a paper with data and stuff if you want. I encourage that as an exercise for you if you want. And then lastly is Gaia. Gaia is probably one of the biggest surveys of stars in our Milky Way, or it is the biggest survey of stars in the Milky Way galaxy. If you want to use it, don't download the entire data set. That's going to be massive, but you can search for data. You can either do it this way, just by like searching for an object name, and it'll pull up a bunch of data that you can download, or you can do it advanced through like what's called ADQL, which is just a form of a coding language called SQL or SQL. They talk about it in 61A if you want to learn more about it. I don't know if I could like, maybe I can just do a little quick example to see. No, it doesn't pull up. Well, regardless, in here you kind of write like some code It's not really like code that we think of like in Python. It's SQL is a declarative programming language, which means instead of telling the computer how to code, like how to do a process that you want it to do, you just tell it what you want, and it figures out how to do it itself, and then it tells you the information you want. So it's finding the best way to give you what you want. It's very similar. It's the kind of like the backbone of what makes things like Amazon work. When you go to search like I don't know, like shoes on Amazon, it all you're doing is putting in an entry, and it tells, like, it's a SQL entry that the server reads and it finds the best way to spit out the information that you want. That's all it is, and it's not very hard to learn. You can learn it in like a couple hours, and you can use it to pull very specific requests of like the type of data you want. But anyway, this is Gaia. You can pull tons of information. If I just search something like M15 and submit a query for it, query is like another word for a search. You'll pull up like lots of information that you can download in the form of like a CSV file, a FITS file, and so on. I understand this is like a lot of information, so my apologies, but we got to keep marching on because there's still a little bit of stuff I want to talk about. And then you can use AstroPy to do this. And if you want to learn how to do that, if you want to use like AstroPy to search for data and pull it into your Jupyter Notebook, you can click on this link, and they have like a tutorial and stuff that you can follow to learn how to do that. Yeah, this is how you acquire data. You use things like Vizier, Sinbad, and Gaia, and then you can use AstroQuery, which is like an AstroPy function / library, and you can use it to pull data, or you can just get your own data. Some people have access to telescopes and stuff, and that's great. But yeah, so that's how you acquire like real physical astro data that people have taken, and you can use it for your own analysis. Other people do simulations. This is more that theoretical side of astronomy that we were talking about. Some people write simulations, and you can use their simulation data to compare to real data. So some notes about simulations: they can be coded or ran by you. A lot of you are trying to simulate something for your final project, and those are usually smaller scale. It's rude to say they're simple, but compared to the other like full-on research simulations that require lots and lots of physics background, they're pretty simple. We often use like software packages, like whole-on codes that people developed that are like 50,000 lines of code minimum. We use their packages, and we can run our own complicated simulations just with the backbone that they wrote. Examples of this might be like something like MESA, which is like one-dimensional stellar simulations if you want to simulate how stars work, or like Athena++. This is like a three-dimensional magneto-hydrodynamic simulation. It kind of produces pictures like this one that you see here. Let me show my laser pointer. Like this one right here is something that you can code with like Athena++, or even something like this or this. These are like magneto-hydrodynamics. They're very, very cool. Really complicated simulations are ran on supercomputers because you definitely can't run it on a laptop. They require lots and lots of computations, and they're expensive. This is going back to that whole applying for time on like a supercomputer or whatever. This is something a postdoc or professor would do. But with that time, they run simulations, or they like analyze big data sets from like big scale simulations, or they run them if they have lots of computational power, like a supercomputer. So what we can usually do as like a layperson, you and I, we can download their simulation data. So like, here's an example of one. This is like Illustris. This is like a full-on cosmology simulation of the entire universe, plus magnetohydrodynamics, plus dark matter, and all that fun stuff. Like literally as many things you could put into a simulation. And like the data files are terabytes. For reference, like a MacBook Pro might have max like a terabyte, like 1 terabyte in its entire computer storage, and that could hold anything you could possibly need. But these, like the data, just the straight up like amount of information in like bits and like numbers and stuff, like the lists themselves of numbers are so big that it literally takes up roughly like terabytes of data, which are crazy. But we'll talk more about this stuff on Wednesday. This is something I like to talk a lot about. So we'll talk more about how simulations work and stuff on Wednesday. But when you have a simulation from theory, oftentimes you want to compare it to real life, right? So you need real data for that. So we spent most of the semester learning how to analyze data, whether or not you realize it or not, learning how to write stuff in Python, how to make plots of data, how to curve fit data and like fit a model to data and stuff like that. That's all really valuable skills that you can use. And when you've analyzed your data, you can compare it to simulations, like theoretical models, and then you get something like this. I don't know if a lot of you were very plugged in, but we took a picture of a black hole a couple of years ago, like the human race. That's pretty impressive. So like this is like actual telescope data of M87, the black hole inside of that galaxy far away. Back literally, it's like 4 years ago. It's kind of crazy. And we compared it to simulations, and you can see that the simulations, like if you blur the simulation a bit, it's literally like the same thing. And there's a lot of analysis that we don't need to go into how they compare them specifically, but if you can analyze the data, you can show that these are like, hey, our theory is perfectly matching up with the observation. And that's amazing. That's like a huge feat. And that's definitely like either Nobel Prize or high end, like good quality research papers coming out of that, that advance, our understanding of the universe. So it's really cool. And then so the last part of research that I just want to talk a little bit about, not really. I guess, does anybody want to answer how they think we write a research paper? What do we use to write a research paper? Specifically in collaboration with others.
LaTeX.
Yeah, LaTeX. And we specifically use a website called Overleaf. Hopefully you're writing your CV on Overleaf and getting used to it, because I promise you, if you're ever going to write a research paper, you're going to need Overleaf. We saw a lot of weird examples of like a word today. I don't know. I guess I got really unlucky, but I promise you, like 90% of people write with LaTeX on Overleaf. It looks so much better and way more professional. So write your papers and stuff on Overleaf in LaTeX, and I promise you they'll look great. And if you want good practice on how to LaTeX really well, I recommend starting to LaTeX your homeworks. It's always it's tough at first, but oh my gosh, it makes I think you get graded less harshly. Like, I'm pretty sure about that. And then two, it's good skill for when you go to write research papers. But yeah, so that's everything I had for today. I hope you all found that interesting. I'll stick around if anybody has any questions, but you guys are free to go. Thanks for coming.
Thank you.
Thank you.
Thank you.
You're welcome. Hey, Roselle, do you have? Oh, okay, yeah, she's gone. Cool. Yeah. Hey, everybody. Again. Oh, that's right. I gotta turn off recording.